viewers, welcome to my YouTube channel. We want to study on chemistry form 3 on the topic nitrogen and its compounds. And our subtopic today, we want to talk about the Haber process. Haber process simply means the large manufacture of ammonia in industry. There are several industries in Kenya where ammonia is being manufactured. So when they are manufacturing the ammonia, they need some raw materials, and these raw materials are nitrogen, and we know very well that nitrogen is being obtained by fractional distillation of liquefied air. That is a topic in form 1, and also in form 3 is a repetition. In form 3 we shall look at how we obtain it using fractional distillation. Number 2 raw material is hydrogen. How is it obtained? It is obtained either by using natural gas or as a byproduct of cracking the long chains of alkanes. Now, that's how we obtain hydrogen and nitrogen as the raw materials when we want to manufacture ammonia. Now, how can we obtain nitrogen using fractional distillation? This is what we looked at in form 1, where air is filtered, and after being filtered is then taken to intake pump. Then it is dust free, it removes some dust, then taken to where we have a solution of potassium hydroxide or sodium hydroxide, where carbon dioxide is free now from air. Then to condensation chamber at a temperature of -25. Then therefore the air is free from water vapor. Of course, it's separated as ice. Then taken to a compressor of 200 atmospheres, together with this is -200 degrees Celsius. Then the 3 gases are being obtained because they have some different in their boiling points. You can see nitrogen has a -106. That means it's going to be distilled out fast because it has a low boiling points compared to argon of -186 and oxygen of -183. And that's how we obtain, of course, nitrogen. Now, how about hydrogen? How is hydrogen obtained? By cracking of the alkanes. Of course, this is a long chains of alkanes. If you heat long chains of alkanes, or by using either heat or catalyst, then you end up having some smaller chains of alkanes and also alkenes together with hydrogen gas. And that is how we obtain hydrogen from cracking of long chains of alkanes. Now, the flowchart above shows the Haber process, how it looks like, and usually in large manufacture of ammonia, you realize that there's some big tanks that represent some chambers that we look at in our flowchart. Of course, a starting point, we are going to start with our raw materials. We have, of course, nitrogen and hydrogen. The 2 are being taken to a purifier, then to a compressor. From the compressor, then they are taken to heat exchanger. Then from the heat exchanger to catalytic chamber of about 500 degrees Celsius. Then from catalytic chamber, it is again taken back to heat exchanger. Then it is only 10% of the liquid plus the unreacted nitrogen and hydrogen of ammonia being just taken back to heat exchanger. We shall see why. Then from the heat exchanger, those products are then taken to a condenser, where we have where the products are being condensed. Then those gases that are being, those gases that don't react, they are again taken to the compressor. condenser, for that is recycling. Then liquid ammonia is taken out, then it is of course collected using some containers in industries and ready for sale. How does it happen? Nitrogen and hydrogen being mixed in a ratio of 1 to 3. The reason being is that hydrogen is more explosive. So if you try to take nitrogen, remember it has a triple bond and it requires some heat, and you realize this reaction is exothermic, and that's why nitrogen is easily can react with hydrogen. So the ratio is 1 to ratio 3. If you write the equation or the chemical equation of how nitrogen reacts with hydrogen, then you realize that the ratio of nitrogen to hydrogen is 1 to 3. So they are passed through a purifier. Then the reason is just to remove the impurities, and these impurities, if they are not removed, then they are going to poison the catalyst which is going to be used in the process. Of course, the dust particles are being removed here through a process we call electrostatic precipitation. Such impurities which are removed so that they cannot poison the catalyst are: number 1, we have carbon dioxide, number 2, we have sulfur 4 oxide, and also the dust particles. Now the mixture of nitrogen and hydrogen is then compressed, that is in between 200 to 500 atmospheres, depending on because in Form 4, the topic in Form 4, we shall look at reaction rates, because even that is rate of reaction can affect equilibrium system of an equation. For example, if the industry want to manufacture large amount of ammonia, they should use some conditions so that they can have large. Number 1 is they should have at least the atmospheric pressure should be around 200 to 500 in between there, so that they can, despite the fact it is very expensive, but amount of ammonia being produced will be very large. Then it is again passed into a catalytic chamber where maintain temperatures of around 400 to 500. Also, this is economical, because when temperatures are very high and the reaction is exothermic, then it favors the forward reaction, that is large manufacture of ammonia, according to a topic in Form 4. Then we have this catalyst that we use in this process is: number 1, we have finely divided iron, which is being used here. It is finely divided iron. Realize that in KLB it is just written iron, but it should be finely divided iron, because when it is finely, it means it increases the surface area for the reaction in this process take place very fast. So in this reaction, we said earlier that is highly exothermic, and of course it sustains the temperature in the catalytic chamber. That's why nitrogen is able to react with hydrogen. Despite, remember that nitrogen cannot react with hydrogen if the temperatures they use is temperatures at room temperature, because room temperature cannot break the triple bonds, so that's why they use high temperatures, and this temperature must be sustained so that the two raw materials may react to form ammonia. And of course heat is produced to show that the reaction is exothermic. In the same flowchart, we saw some heat exchanger. It has some functions. From the word itself, some heat is exchanged, where the hot mixture of ammonia and some gases have not have reacted are passed into the heat exchanger, where cooling takes place. So the one function of a heat exchanger is for cooling. Number 2 function of heat exchanger is used to preheat the incoming mixture of nitrogen and hydrogen. This makes the process, of course, economical. Then we have ammonia produced is of course liquefied in the condenser and stored in the cylinders. The gases which are not have not reacted are just recycled, and therefore of course it reduces the wastage of such kind of gases. The yellow ammonia is high at a higher pressure and low temperatures. You saw the temperatures we are using were around 450, and of course for the pressure were around 200 to 400. That means if the pressure increases, it favors the forward reaction. If that is of course temperatures are low, it favors the forward reaction since the reaction is exothermic. However, it is expensive to maintain such high pressure, but at the end of the day, large amount of ammonia is produced in that industry. When used, of course, there is another disadvantage. When used low temperatures, despite the fact that they produce large amount of ammonia, there is a disadvantage. This disadvantage is that at low temperatures, the reaction is very slow. So to reduce the production cost of the optimum condition of this, of around 500 degrees Celsius or 200 atmospheres, and the ion catalyst, of course the ion catalyst is employed so that it can increase the rate of reaction despite of the low temperatures. Lastly, we want to see the uses of ammonia. After ammonia is being manufactured, stored in cylinders, then automatic we have the uses of ammonia. Number one use of ammonia is act as a fertilizer. Ammonia is a fertilizer itself. Number two, it can be used in manufacture of course, nitrogenous fertilizers. A good example we usually use is urea. We have some like ammonium sulfate, all those ones. You can see ammonia can react to sulfuric acid to form ammonium sulfate, which is a fertilizer, that is nitrogenous fertilizer. Next use is that it acts as a refrigerant, e.g. in large manufacture of refrigerating plants such as ships and warehouse. That's where we use ammonia to act as a refrigerant. Number three, we have it can be used to soften, of course, hard water. Ammonia can be used to soften hard water. Number four, ammonia can be used in the removal of grease, stains. If your cloth is stained, you can use ammonia to remove such permanent stains, especially white clothes. You can use ammonia to remove such kind of stains. And lastly, it can be used in manufacture of hydrazine, of course, which is used in the rocket fuel. Thank you very much. That is our study today about Haber process. Next time we shall look at the questions concerning Haber process. This question usually come in paper 2 chemistry, and is very simple when you follow the flow chart that we have looked at. And please subscribe to my channel and also share to your friends so that they can get the information. Thank you.